Let us now again design one more modulo counter, say modulo 6 counter, modulo 6 counter. So again I'll tell you the number of steps which has to be followed. The first one is to decide the number of flip-flops. 2 raised to power n is equal to m. So 2 raised to power n is equal to modulo 6 is given. So now if you take n is equal to 2, m will be equal to 4. Of course not possible. N is equal to 3, if you take, m will be equal to 8. So in a modulo 8 counter you can easily design modulo 6 counter. So in case of modulo 6 counter, how many flip-flops we have to use? We have to use 3 flip-flops. So what will be the how many outputs? 3 outputs, C, B, A, and this will be clock. And if it is a modulo 6 counter, it should count from 0 to 5. So the state will be 0, 0, 0, and 5 is 1, 0, 1. Total number of discrete states will be 6, and at the 6th condition it should reset. So what is the 6? 1, 1, 0, 6 state. So this is the point where the circuit should reset. So now what happens is, in the modulo 10 counter we designed 4 flip-flops. Now we require only 3 flip-flops. So the circuit will be like this. This is the modification which I am going to make in the circuit for this is your MSB. Now C is your MSB. Now you have to connect clear terminal of all the flip-flops. Output of the clear terminal should be connected to the NAND gate. NAND gate's output should be connected to the clear terminal, and the input for the NAND gate you have to decide by this bracket. You have to see which variable is 1, C and B are 1. So you connect C and you connect B. So now let us try to understand the working using the truth table. So see the condition. What happens is, as it is a normal binary counter, with each applied clock pulse the count will increase. Initially CBA is 0, 0, 0. So B and C both are 0, and if it is 0 the output of the NAND gate will be 1, and if it is 1 the clear terminals are deactivated. It will have no function to play in the operation of the flip-flop. So with each applied clock pulse the count will increase. So first clock pulse 0, 0, 1. Again what you can see, C and B is 0, the output of the NAND gate will remain 1. Second clock pulse 0, 1, 0. Now C is 0, B is 1, but still if any one of the input is 0, the output of the NAND gate will be 1. So clear terminal will be deactivated. Third 0, 1, 1, it remains same. 4, 1, 0, 0. Now C has become 1, B is now 0. So if any one of the input is 0, the output of the NAND gate is 1, clear terminal is deactivated. Fifth 1, 0, 1. Sixth 1, 1, 0. At this point, sixth, both the inputs becomes 1. So B and C both are 1. So output of the NAND gate will become 0. As soon as it becomes 0, all the clear terminal is activated, and the purpose of clear terminal is to reset Q output. Reset Q output means all the Q outputs will become 0. So at this point all the Q outputs will be 0. So the circuit will now count from 0 to 5. The total number of discrete states is 66, and that is why it is called as modulo 6 counter. So you should be able to understand that for different modulo counter different number of flip-flops are used, and it will have a different conditions for reset. So the reset conditions has to be checked like this, and then the variables which are 1 at that particular point should be connected to the input of the NAND gate. So this is how a modulo 6 counter and modulo 10 counter works. Thanks. The next circuit and the last circuit of the counter is 3-bit synchronous counter. So 3-bit synchronous counter. Of course, you remember when we started counters, we segregated or we modified the counters into two types, asynchronous and synchronous. synchronous counters where all the flip-flops are clocked at the same time, so they will change their state at the same time. Asynchronous counter, the counters where it is a counter where the flip-flops are clocked at a different interval of time, and therefore they are changing their state at different interval of time. So till now all the counters which we have studied were asynchronous counter because they are very easy to design, less hardware is required, less is the cost. So there will be only one circuit in your course to understand the 3-bit synchronous counter. Of course, if you can say 3-bit, that means it will be 3 flip-flops. So 3 JK master slave flip-flop working in toggle mode. So see how it has to be designed. As I said, all the flip-flops should be changing their state simultaneously. Only then that counter will be called as synchronous counter. So now say the first flip-flop, this is J, this is K, Q, Q bar, preset and clear terminal. Again the first flip-flop will be clocked directly. J and K is 1. Now the output of the first is connected through AND gate. So this is A, which is your LSB. Now the output of the AND gate is connected as clock input for the second flip-flop J, K, 1, 1, preset, Q, Q bar, this is clear. Now the clock pulse which is given to the first flip-flop, the same clock pulse will be available through an AND gate to flip-flop 2. Similarly, in the second step, the second flip-flop's output is connected to AND gate, and the clock pulse which is given to the first and the second flip-flop will be available for the third also. But for third, it will come from AND gate. It will come from AND gate 2. For first, it will come from AND gate 1, and the output of the AND gate will be connected to the clock input of the third JK master slave flip-flop, which is working in toggle mode, Q bar. So this is your C. So this is your third flip-flop, this is your second, this is first. So what you can see is for the first flip-flop, direct clock pulse is applied. That means every time there will be a clock here going from 1 to 0, the flip-flop will toggle first, second, third, fourth, like this. For the second flip-flop, the clock depends upon the AND gate. If the AND gate is activated, the clock pulse which is given to the first clock pulse will be available for second also, it will be available for the third also, but it depends upon the AND gate. If the AND gate is activated, this clock pulse will reach to the second flip-flop. If the AND gate is activated, the clock pulse will reach to the third flip-flop. So what is the condition for the AND gate to be activated? The two inputs are, the first one is clock, the other one is A. So it will be A dot clock, where clock dot indicates AND operation. Third flip-flop, A is also input, B is also input, and clock. So A dot B dot clock. So this is the case. So this is how as you can see, the circuit becomes complicated, more number of AND gates are required, so the cost also increases. Now let us try to understand the working. So this is clock C, B, A. Let's say initially activating clear terminal of all the flip-flops, so we make CBA is equal to 0, 0, 0. Now see, A is 0, B is also 0. So for the first AND gate, one input is 0. For the second AND gate, both the inputs are 0. This will be deactivated, this will be deactivated. And when you apply the first clock pulse, which flip-flop is getting the clock? सेकंड को भी नहीं मिलेगा, थर्ड को भी नहीं मिलेगा. ये जो क्लॉक आप दोगे ये सिर्फ फर्स्ट फ्लिप फ्लॉप को मिलेगा. इसका मतलब सिर्फ फर्स्ट फ्लिप फ्लॉप टॉगल करेगा, सेकंड और थर्ड नहीं करेंगे. मतलब पहला क्लॉक पल्स जब खत्म होगा, द स्टेट विल बी 0, 0, 1. नाउ A is 1, B is still 0, A now has become 1. But for this AND gate, out of this 2 input, 1 input is 0, so this will be still deactivated, but this is now activated. So when you give the second clock pulse, of course it is given to the first, and as this AND gate is activated, the same clock pulse will reach to the second flip-flop also. So second flip-flop will toggle, but third is deactivated. The second AND gate is deactivated, that means third flip-flop will not change its state. So the state at the end of the second clock pulse will be C is 0, B changes, A changes. So it will be 0, 1, 0. Now third clock pulse, again you see what happens now. A has become 0, B is 1. So as soon as A is 0, again the first AND gate will be deactivated. B1, A0, still the second AND gate is deactivated. So when you give the clock pulse, second and third flip-flop will not get the clock, only the first flip-flop will get, and it will change its state. So 0, 1, 1. So what you can see is it is exactly counting like 3-bit up counter, 0, 1, 2, 3. So the condition remains same, 1, 1, 0, 0. At the end of the fifth clock pulse, it will be 1, 0, 1, 6 clock pulse, 1, 1, 0, 7 clock pulse, 1, 1, 1, and 8 clock pulse. Again it will go back to its initial state. So the circuit operation remains same. The only difference is that all the flip-flops changes their state simultaneously by introducing this AND gate. So this is how a 3-bit synchronous counter works. Again, the disadvantage is the circuit becomes complicated. Second, more number of hardwares are required. And third, therefore, the cost increases. So this is all about counters. I hope you have understood. Hello students, the next application of flip-flop is shift registers. Registers, not register. Register is a component which is used for blocking the amount of current which is flowing in the circuit. Register, of course, it's like your register. What is the use of your register? You store information in your register and retrieve data whenever required. Of course, you write your notes on your register, and whenever it is required, you read the data from your register. So exactly on the same way, if you want to store binary data and retrieve the data later, you have to use register. Of course, then we can define the register as, of course, it will be a binary data, and to store binary data we have designed flip-flops. So it is a group of flip-flops used to store binary data, which is called as register. But what is shift register? The data which is stored in the register, if it can be moved 1 bit towards right or 1 bit towards left with the applied clock pulse, the circuit is called as shift register. So when you define, we say it is a group of flip-flop used to store binary information, which is, we can say, as data, binary information which will be in the form of 0 and 1. So it is a group of flip-flop used to store binary information, and the data stored can be shifted 1 bit towards right or left with the applied clock pulse. So if you can interpret this thing, this is nothing but a shift register. It is a shift register. Of course, we will be designing both right shift register, left shift register, and a circuit which performs both as right as well as left shift register. So for that, we will be using D flip-flop. So for that, please make sure that you go back to the D flip-flop videos, check the D flip-flop contents. Just for your information, I'll give it is clock initial condition Q is equal to 0, Q bar equals to 1, and clock D, Q and Q bar. If clock is 0, there will be no conditions at D. That means input at D will be going into don't care condition and there is no change. When the clock is 1, when the clock goes 1 and if D is 1, the output sets. And if clock goes 1 and D is 0, clock is reset. That means whatever you are giving at the input, same will be the output, same will be the Q output. If D is 1, Q is 1, if D is 0, Q will be 0. You need these conditions to understand the circuit which we are going to design. So first circuit which we will design is 3-bit right shift register. 3-bit right shift register. So if 3-bit, 3 flip-flops will be needed, 3 D flip-flop will be needed. So we will draw 3 D flip-flops. This is the first input D, Q, Q bar, second D, Q, Q bar, third D, Q and Q bar. Now output of the first is directly connected to the input of second. Output of second is directly connected to the input of third. So this is first, this is second, this is third. All these flip-flops will be clocked simultaneously. That means all the flip-flops will change their state at the same time. Same clock pulse is given to all the flip-flops. No AND gate, no additional hardware. If the clock pulse is given, this will change, and this will change. So let this be A, let this be B, and let this be C. So this is the condition, and input we are applying to the first flip-flop. This is where the input will be applied. Say input is 1 0 1. Now of course we will have preset and clear terminals. So preset and clear terminal. Let us try to understand the working of this 3-bit shift register by using a truth table. Clock A, B and C. Let's say when clock is 0, we will activate clear terminal of all the flip-flops so that output of all the flip-flops is 0 0 0. So now when A is 0, this will be the input for the second flip-flop. B is 0, this will be the input of the third flip-flop, and for the first flip-flop the first data will go inside, which is 1. See, I am predefining the inputs because the flip-flop will change their state at the same time. So second flip-flop will depend upon previous condition of A, which is 0. Third flip-flop will depend upon the previous condition of B, which is 0. Not after changing, before changing the condition, that will be the input. So for the first flip-flop the input is 1, for the second 0, third is 0. So at the end of the first clock pulse, what happens is if D is 1, Q will be 1, if D is 0, Q will be 0, if D is 0, Q will be 0. So the state at the end of the first clock pulse is 1 0 0. That means what you can see is the first data has entered into the group of flip-flops. That means it has entered into the register. Now at the second clock pulse, see now what happens is, what is the previous state of A? Now A is 1, B is still 0, and the input for this will now be 0 for the first flip-flop. So when you give the clock pulse, again all the flip-flops will change their state simultaneously. What is the input for the first? 0, so the Q output becomes 0. What is the input for the second? A is 1, so B will become 1, and B is 0, so C will be 0. Now what you can see is the data from A has been transferred to B and new data has entered into A. Similarly third, now A is 0, B is 1, and now the next input will be entered into the first flip-flop, that is 1. So for first flip-flop the input is 1, second 0, third is 1. So in the next clock pulse the output of the first will become 1, second will become 0, and third will be like this. So data from B has shifted to C, data from A has shifted to B, and new data has entered into the first flip-flop. So what you can see from the truth table is, with each applied clock pulse, the data is shifting one bit towards right and new data is being entered into the first flip-flop. So with each applied clock pulse, the data is getting temporarily stored in the flip-flop. At the same time, it is shifting one bit towards right. Therefore, it is called as 3-bit right shift register. The next circuit is 3-bit left shift register. Exactly on the same lines of 3-bit right shift register, we will now design 3-bit left shift register. So the circuit diagram remains exactly the same, but the only difference will be, in case of right shift register, input was applied to the first flip-flop. In case of left shift register, the input will be applied to the third flip-flop. So we will write input over here. In case of right shift register, output of first was connected to the input of second, output of second was connected to input of third, so that data can move from 1 to 2 and 2 to 3. But in case of left shift register, output of 3 will be connected to the input of second. Output of second will be connected to the input of third, input of first, so that data from third, 3 will go to 2, from data 2 will go for 1. So let us try to understand the operation by understanding the truth table. Let's say initially, again activating clear terminal of all the flip-flops, say the output of all the flip-flops is 0. Let the input data be 1 0 1. So the first input will be available for the third flip-flop. At present, what is the output of C? C is 0, which will be the input for second flip-flop. What is B? B is 0, which will be input for the first flip-flop. So input for the first flip-flop is 0, input for the second flip-flop is 0, and input for third flip-flop is 1. So at the end of the first clock pulse, what is the data? 0 0 1. New data has entered into the third flip-flop. It is moving from left now. Now the output C has become 1. So if C is 1, the input for the second flip-flop will become 1. Then 0 will be, and the output of the second is 0. So input for the first is still 1. So at the end, before applying the second clock pulse, what is the state here? Input for the first flip-flop is 0, input for the second flip-flop is 1, and input for the third flip-flop is the new data, which is 0. So at the end of the second clock pulse, the state will be 0 1 0. That means 1 at C has transferred to B and new data has entered into C. So now C is 0, so this is 0, so input for the second flip-flop will be 0. B is now 1, which is input for the first, so this is 1. So with the next applied clock pulse, what is the input? For first flip-flop 1, for second flip-flop 0, for the third flip-flop now new data is available, this 1 will be transferred. So at the end of the third clock pulse, it will be 1 0 1. That means this 1 from B has transferred to A, 0 from C has transferred to B, and new data has entered into C. So with each applied clock pulse, the data is now moving 1 bit towards left. So this is 3-bit left shift register. I hope you have understood. Converters. So under this heading converter, we will try to understand two types of converters. One which is called as D to A converter and A to D converter. So when you say D to A, that means digital to analog. And if you say A to D, it is analog to digital converter. So this is what we will try to understand in this chapter. This chapter is very small and we have only 5 circuits, 2 circuits of digital to analog converter and 3 circuits of analog to digital converter. So that's all, and this chapter will have a weightage of around 15 marks. So it is very, very important with respect to your exams. So now what exactly we mean by digital to analog or analog to digital? Let us try to understand. First, you understand what exactly I mean by digital or analog. So when I say digital signal, that means a signal which has only 2 discrete states. So if you consider it as voltage level, so the voltage level, say this is plus 5 volt and say this is minus 5 volt. So if you consider according to voltage level, so the digital signal will have only two levels. What you can see? Plus 5, minus 5, plus 5, minus 5, plus 5, minus 5. And any value which is positive will be considered in digital as 1, and any negative value will be considered as 0. So this is how the signal will vary: 1 0 1 0. So though it will have only two discrete states, 1 and 0. Now let us talk about analog signal. So the analog signal has a continuous varying signal. So what you can say is, if I consider this voltage as 0 volt and this value as plus 5 volt and this value as minus 5 volt, what you can say is, with respect to time, the voltage level will be continuously changing. It will not be at discrete state. It will be having different levels, say 2 volt, 3 volt, 4 volt, 5 volt. Like this, the output voltage will continuously be varying with respect to the time. So this is what is analog, this is what is digital. So digital signal are those signal which changes its state at discrete level, 0 and 1, 0 and 1, and whereas analog signal, it will be continuously varying signal with respect to time. So this is the time reference. So with respect to time, analog signal will be continuously varying. So now where you want to understand digital to analog or analog to digital, that means where you are going to use this type of circuit, digital to analog or analog to digital. I'll give you a very good example. Say you are measuring pressure, you are measuring temperature, or say you are measuring force. All these quantities are analog in nature. Why I say analog in nature? Because whenever you measure temperature, pressure, force, what happens is the signal which you are going to get will be continuously varying signal. That's why it is in analog in nature. And suppose this signals has to be, or this quantities has to be measured and put it into, say, stored into computer. Then computer knows only digital language, only binary information. So then what you have to do is, you have to convert this analog signal back to digital, right? So that the data gets stored into the computer. So this is the one use, analog to digital converter. And next what we do is, suppose I'll give you an example. There is a burner completely filled with a liquid which is getting heated up by a vessel is there completely filled with say some liquid, and a burner is there which is heating up the liquid. We have to maintain the temperature at a certain level. So what we will do is, we will be continuously measuring the temperature and we will be storing it to the computer. So we will require analog to digital converter. Now suppose if the temperature goes beyond the range, you have to keep the temperature of the solution constant. So what you have to do is, if the temperature goes beyond the range, the burner should be switched off. But who will do that? Of course, the computer. The computer will understand the logic, and what it will do is, if the temperature goes beyond a certain range, the digital signal will generate a signal which will turn off the burner. So when the digital signal has to generate a signal which has to be turned off the burner, it will be converted back into analog. So we have a digital to analog circuit. Now let us try to understand what basically we are going to do. See, the binary values will be like this: 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1. So if I take this value on x-axis, there will be corresponding to each of this binary value, there will be a corresponding voltage level: 1 2 3 4 5 6 7 8. So there will be a corresponding voltage level for each of this binary values. So that is what we are going to do. So let's say this is 1 volt, this is 0 volt, this is 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt. So corresponding to each binary value there will be a voltage level. So what we are going to do in converting digital to analog, we are converting a binary information into an analog voltage, so that is what we are going to do in digital to analog converter. And in analog to digital, voltage will be there, and for that voltage corresponding binary value we will get at the output. So this is what is analog to digital and digital to analog converter circuits. The first converter we will try to understand is a D2A converter called as weighted resistor type D2A converter. Of course, resistor here means the resistance. Weighted resistor, let us try to understand what exactly we mean by weighted resistor. Now what we are doing is we are converting a digital into analog. That means input will be binary data and output will be a voltage level. So we have to for this circuit we have to derive an output voltage equation, which converts a binary value into analog voltage. So that is what we will do. Now before that, before going to the circuit diagram, let us try to understand what exactly we mean by weighted resistor. Now suppose there is a binary number, say 1111. So of course you know that this number has a certain weight, and if it is a binary number, the weight will be 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. So this is what is the weight of this number system. So what is weight? Then it will be 1 and 2, this is 4 and this is 8. So weight of corresponding bits, this is of course we will be saying as LSB, this is MSB. MSB has the highest weight, LSB has the lowest weight. So this is the weight of the binary number. So now when you are designing, now we will design a 4-bit weighted resistor type D2A converter. So now what I want is, in the circuit diagram, what I want is, I want 4 resistance. Now 4 resistance, say this is R1, R2, R3 and R4. 4 resistance we will use because we are having 4-bit, we have to design a 4-bit weighted resistor. Now the term weighted, you have to make sure that the resistance which are connected should have a ratio of, that means weight ratio of 8:4:2:1, starting from MSB to LSB. So what we will do is, the resistance value which we are going to select, of course will define the current which will be flowing, and you know voltage is equal to current multiplied by the resistance. So the current will be V upon R. So the current which will be flowing through R1, say R2, say R3, say R4 be I1, I2, I3 and I4. Now the current which will be flowing through the resistance should be in the ratio of 8:4:2:1. That means maximum current should be at I4, minimum current should be at I1, and the ratio should be 8:4:2:1. So suppose if I select the value of R1 as R, what will be the next resistance value? R2. See, what happens is, from I1, this is the LSB, this is I4 MSB. So when the current should increase, it should be in the ratio of 1:2:4:8. Current should keep on increasing. So current increase means resistance should decrease according to this equation. So resistance should be decreased. So what should be the ratio of resistance decrease? If this is R, this should be R by 2. If this is R by 2, the next will be R by 4. And the next resistance will be R by 8, starting from LSB to MSB. Let the voltage digital values which we are going to apply, say that will be, say V1, V2, V3 and V4. These are the 4 voltage which we will be applying at the input. So this will be the digital data, and as soon as a voltage is applied over here, current will flow. Current will flow in the ratio of 8:4:2:1, starting from MSB to LSB. Say MSB V4 is MSB and V1 is LSB. So this is how the circuit has to be designed, and what you have to do is the entire circuit will be connected together, say at point P, and from there we will take one more resistance across which we will take the output voltage. So the resistance in any electronic circuit, the resistance across which the output voltage is taken is called as load resistance. We specify it as RL, and the current flowing through that load resistance is called as IL. So we specify it as IL. Okay, load current, load resistance, load current, that means the resistance across which the output voltage will be taken. Okay, so this is the basic circuitry for 4-bit weighted resistor type D2A converter. Suppose if a 3-bit weighted resistor is asked, so instead of 4 resistance, we will using only R1, R2, R3. That means the resistance value will be R by 2, R by 4. And if it is a 5-bit weighted resistor, then you have to add one more resistance whose value will be, the ratio will be next one, then it will be 2 raised to power 4, that means 16. So the ratio will be 16:8:4:2:1. The next resistance value will be R by 16. So this is how the modification has to be done. So this is the circuit diagram for 4-bit weighted resistor type D2A converter. Let us now derive an output voltage equation which converts the digital value or the binary information into analog voltage. So in this circuit, what you can see is we are going to take the output voltage from this. So we have to obtain an output voltage equation. So according to simple Ohm's law, if we start, we say V0 is equal to, from the circuit we can see V0 is equal to, according to Ohm's law, voltage is current multiplied by resistance. So V0 is equal to IL multiplied by RL. Let this be equation number 1. IL multiplied by RL. Now applying KCL at point P. Now this term KCL, of course it was in the 11th standard. I don't know how many of you remember or how many of you have studied this topic called as KCL. It is called as Kirchhoff's current law and Kirchhoff's voltage law. There are two laws which are there, and it is used to solve electronic circuits, to simplify electronic circuits. This is what, so it's very easy, very basic law has to be studied, and I hope you must have gone through this in physics also. There will be in some topics you need to have an understanding of KCL. See, please remember, or please make sure that you're writing it down now itself. KCL is, in an electronic circuit, a node. A node means a point in electronic circuit where there is 2 or more branches. Of course, if you take this point as P, how many nodes, how many branches are there? Current is flowing from I4, I3, I2, I1, and it is flowing through IL also. Okay, so a point in electronic circuit from where there are 2 or more branches called as node. So if you apply KCL at point P, the KCL says that the statement is all the current entering into the node is equal to all the current flowing away from the node. So by the arrow mark you can see how the current will flow. Current will flow from positive to ground. Potential is applied over here, so current will flow like this, right? So I1, I2, I3, I4 are flowing into point P, and the current which is flowing out of point P is IL, and what the statement is, total current entering into the node is equal to total current flowing away from the node. So when you apply KCL at point P, we can say IL is the current flowing away from the node, and current entering the node is I1 plus I2 plus I3 plus I4. So this is I1 plus I2 plus I3 plus I4. Let this be equation number 2. I hope you have understood that particular step. Now substitute the value of 2 in 1. Substitute the value of 2 in 1. So what is the value of V0 now? It will be I1 plus I2 plus I3 plus I4 multiplied by RL. Let this be equation number 3. Okay. Now we have to calculate the total equivalent resistance of the circuit. Whenever in an electronic circuit you calculate the resistance value, total equivalent resistance of the circuit, all the voltage source should be short circuited to ground, or all the voltage source should be connected to ground. So here what are the voltage source? V1, V2, V3, V4 are the voltage source, and this voltage source are supposed to be connected to ground. Ground means this point. So all the 4 resistance, just imagine that this 4 resistance has been tilted and it is connected to ground. So what happens is this 4 resistance R1, R2, R3, R4 comes in parallel with RL. I hope you have understood what I am trying to say. As I said, whenever you calculate the total equivalent resistance of the circuit, the voltage source should be connected to ground. So imagine this resistance to be tilted like this and connected to ground. These 4 points connected to ground. So what happens? This 4 resistance comes in parallel to RL. And what is the formula for parallel resistance? 1 upon RL is 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon R4. And if you take the value of RL, it is 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon R4. So this is the value of RL. What I'm going to do is I'm going to use this formula directly here. Well, I'll say that now by total resistance equation across RL, we get, what we get is, now V0 is equal to I1 plus I2 plus I3 plus I4 multiplied by what is RL? RL is 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon R4. So this is the equation. Now what is I1? I1 is the current flowing through R1 when V1 is applied. So can I write I1 is V1 upon R1, right, according to Ohm's law. Similarly, I2 is the current flowing through R2 when V2 is applied. So I2 will be V2 upon R2. Similarly, I3 is V3 upon R3 and I4 is V4 upon R4. So substituting that value, what we will get is V0 is equal to V1 upon R1 plus V2 upon R2 plus V3 upon R3 plus V4 upon R4 multiplied by 1 upon, what is the value of R1, R2, R3, R4? Weighted resistor R, R by 2, R by 4, R by 8. So let's substitute that value, 1 upon R plus 2 upon R plus 4 upon R plus 8 upon R. Of course, 1 upon R1 is R, 1 upon R2 is R by 2, so 2 will go up. So it will be 2 by R, 4 by R, 8 by R. Now, substituting the same value over here also, so V0 is equal to, what we will get is V1 upon R plus R2 is R by 2, so it will be 2V2 by R plus 4V3 by R plus 8V4 by R, and this will be multiplied by R by 15. 1 plus 2 plus 4 plus 8 is 15. R will go up, so it will be R by 15. So the output voltage equation V0 will be V1 plus 2V2 plus 4V3 plus 8V4 divided by R multiplied by R by 15. RR gets cancelled, so output voltage is 1 upon 15 V1 plus 2V2 plus 4V3 plus 8V4, where V1 is LSB and V4 is MSB, and this is the output voltage equation for a weighted resistor type D2A converter, for a 4-bit weighted resistor type D2A converter. Using this equation, we can easily convert a binary value into analog voltage. That means digital signal into analog voltage. Next, we will try to apply that formula to solve the problems. As I said, we will be converting a digital value into binary information into analog voltage. First, you write the formula. The formula is V0. See the question has been asked in a way, in a weighted resistor type D2A converter, 0 corresponds to 0 volt. That means the digital value which we are going to give as input will have only two levels, as I told you in the previous video, in the video, where discrete levels are there, plus 5 volt or minus 5 volts. Only two values will be there. So any positive value will be considered as 1 and any negative value will be considered as 0. So that can be any voltage. 0 can be 0 volt, 1 can be 5 volt, 1 can be plus 5 volt, 0 can be minus 5 volt, 0 can be 0 volt, 1 can be 15 volt, 1 can be 10 volt, 0 can be 0 volt. So such type of various combinations can be used in the logic circuits, but the standard value is for 0 0 volt, for 1 5 volts. This is what we have mentioned in the problem. In a weighted resistor type D2A converter, 0 corresponds to 0 volt and 1 corresponds to 5 volt. Calculate analog output voltage for binary value 0011, 1000 and 1101. So let us try to understand how the problem has been solved. The formula 1 upon 15 V1 plus 2 V2 plus 4 V3 plus 8 V4, and where V1 is LSB, V4 is MSB. Make sure that you are writing this always properly. Next is the first number. We will take 0011. So in this binary number, you can easily identify which is LSB and which is MSB. So this is your LSB and this is your MSB. So this LSB is nothing but V1. So this is V2, this is V3 and this is V4. And what we say is 0 corresponds to 0 volt and 1 corresponds to 5 volts. So wherever you are writing 0, you have to substitute with 0 volt, and wherever you are writing 1, substitute with 5 volt. So the formula next will be V0 is equal to 1 upon 15. 1 upon 15. What is V1? V1 is 1 and 1 corresponds to 5 volts. So we will write 5 plus. Next V2. V2 is 1. So V2 is 1 and 1 corresponds to 5 volts. So 2 into 5 plus. What about V3? V3 is 0. So 4 multiplied by 0 will be 0. And next V4. V4 is also 0. So 8 multiplied with 0 will be 0. So V0 is equal to 1 upon 15 multiplied by 2 5 is 10 plus 5 matlab 15. So that value will be V0 is equal to 1 volt. So for binary value 0011, the analog voltage is 1 volt when 0 corresponds to 0 and 1 corresponds to 5 volts. So this is how we have to solve. So similarly, what you have to do is you have to take this number 1000 and 1101 and you have to solve and get the answer for that particular numbers. I hope you have understood. In the assignment thing, I will be giving you more number of problems so that you can solve and understand exactly how this circuit has to be, the numericals has to be solved for weighted resistor type A to D D2A converter. Thank you. Hello students, in this video let us try to solve few more examples of weighted resistor type D2A converter. In the previous video, the example which we took, we considered 0 as 0 volt and 1 as plus 5 volt. Any higher voltage is considered as 1 and any lower voltage is considered as 0, but the values of the voltage can vary. For example, in this numerical we have mentioned, in a weighted resistor type D2A converter, 0 corresponds to minus 5 volt and 1 corresponds to plus 5 volt. Calculate analog output voltage for binary data 0 1 1 1 1 0 0 1 and 1 1 0 1. So here the voltage levels has changed. Of course, the analog voltage will change accordingly, right? So you have to get used to it. You have to see the voltage level and work accordingly. So first step is to write the output voltage equation. V0 is equal to 1 upon 15 V1 plus 2 V2 plus 4 V3 plus 8 V4, where V1 is LSB, V4 is MSB. Make a habit of writing this LSB and MSB so that there should not be any confusion. Now the first problem which has been given as 0 triple 1. So in that, this 1 is the LSB. So this is V1, this is V2, this is V3 and this is V4. And what is 0? 0 corresponds to minus 5 volt and 1 corresponds to plus 5 volt. So wherever you see 0, you have to substitute minus 5. Wherever you see 1, you have to substitute plus 5. So V0 is equal to 1 upon 15. What is V1? V1 is 1. 1 corresponds to 5 volts. So we will write 5 there. Then what is V2? V2 is again 1. 1 corresponds to 5. So it will be 2 multiplied by 5 plus. Next V3. V3 is again 1. So it will be 4 multiplied by 5 plus. And then V4 is 0, and what 0 is? 0 corresponds to minus 5. So it will be 8 multiplied by minus 5. So now the multiplication has to be carried out. So this will be 1 upon 15, 5 plus 10 plus 20, and this value will be 8 minus 8 multiplied by minus 5, that will be minus 40. So this is 35 minus 40. The answer will be V0 is equal to 1 upon 15 multiplied by minus 5. So 5 multiplied by 3 is 15. So that value will be minus 1 upon 3, and that minus 1 upon 3 can be written as minus 0.33 volt. So this is the answer for the binary value 0111. Similarly, substitute for 1001 1101 and get the answer.